Imagine this, an electron orbiting the nucleus like a planet around the sun. That's what Rutherford proposed. But here's the twist. If Fx is equal to Fx, that were true, the electron should lose energy and spiral into the nucleus in a fraction of a second. Yet atoms are stable. So what was missing? Rutherford's model gave us the structure, but not the why behind atomic stability. This mystery set the stage for deeper discoveries where light, energy, and the tiniest particles of matter would tell a new story.
Let's talk about light, not just what we see, but what it is. Light is part of the electromagnetic spectrum, a grand orchestra of waves, from slow, rumbling radio waves to the sharp, high-energy gamma rays. Each wave travels at the same incredible speed, 3.0 times 10 to the power 8 meters per second, the universal speed limit of light. But what makes each type of radiation different? Their wavelength and frequency. And this distinction is the key to the quantum world. Let's decode the language of light. Wavelength, symbolized by lambda, lambda is the distance between wave peaks. Frequency, denoted by nu, nu is how many waves pass a point per second. The equation that binds them is c equals nu times lambda, where c is the speed of light. Here's a real example. Yellow light has a frequency of 5.17 times 10 to the power 14 Hz. Calculate its wavelength, which is equal to 580 nanometers. That's the exact color our eyes see in a sodium flame. Now let's shift to something groundbreaking. In 1900, Max Planck said, energy isn't continuous, it comes in tiny, indivisible packets called quanta. The energy of each quantum is given by E is equal to h times nu, where E is energy, h is Planck's constant, 6.626 times 10 to the power minus 34 joule-seconds, and nu is frequency. This idea explained why hot objects emit specific colors, not a blur of energy. This was the beginning of quantum physics, a world where energy leaps, not flows. Planck opened the door, and Einstein kicked it wide open. In 1905, he showed that light could behave like a stream of particles, each called a photon. When light hits a metal surface, electrons are instantly ejected, but only if Fx is equal to Fx, the frequency is high enough. No matter how bright the light, if Fx is equal to Fx, its frequency is too low, nothing happens. Einstein described this with kinetic energy is equal to h times nu minus h times v naught, where nu naught is the threshold frequency. It proved something radical. Light is both wave and particle. A dual identity that changed everything. Let's look at the hydrogen atom under a prisma. Instead of a rainbow, we see distinct colored lines, a line spectrum. Each line corresponds to a jump made by an electron from a higher to a lower energy level, releasing energy as light. The famous Balmer series, visible to our eyes, follows the equation 1 by lambda equals r times 1 by 2 squared minus 1 by n squared. Here, r is Rydberg's constant, 1.097 times 10 to the power 7 per meter. This was clear proof. Electrons exist in fixed energy levels and they only emit light when they jump. So, let's connect the dots. We discovered light is quantized, electrons absorb and emit energy in jumps, atomic spectra are evidence of discrete levels. Enter Niels Bohr. In 1913, he proposed a model where electrons revolve in stable, quantized orbits and only jump between them by absorbing or releasing a photon. Bohr's theory explained the hydrogen atom perfectly and laid the foundation for everything we now call quantum mechanics. In our next episode, we'll dive deep into Bohr's model itself, his postulates, equations, and how this changed chemistry forever.